Well, good afternoon and welcome to week 4 for our statistics class. And we've already gone over our seating chart, so I want to begin, as I often do, with a little bit of statistical graphing and our COVID-19 update. These are some numbers or a bar chart that we've seen previously on the MSU website. And what you may notice if you follow along is that the style of presenting these bar charts has changed. And so now, instead of tracking the last 7, 8 previous weeks, it starts at the first week after school began. Meaning we don't have a baseline of where were the numbers before school began. We're only seeing those numbers in reference now to the week after classes began. And we also see that the y-axis has changed. In our first example, the y-axis goes to 150. Now our y-axis stretches to 450. However, I did take the time to correct this bar chart, to put it in context, so that we can now see the pattern. And as we look at this new pattern, we see that in fact those bars are much higher in reference to previous bars. And this gives us a clearer picture of the data. So again, this has always been about statistical graphing, displaying data honestly or in a way that tells us the story. And in this case, you get to make a decision as to whether you like the old style of reporting or the new style of reporting. Personally, I like to get a larger time series picture so that I can see change over time rather than a shorter time frame. Another way that the data have been presented more recently is through this bar chart that splits out the number of cases from residential students, off-campus students, faculty, and staff. Now, as I look at the numbers, I see that the numbers for faculty and staff are very low, a lot of zeros and ones, and that makes me feel good because I'm faculty. On the other hand, there's nothing about faculty status that protects you from COVID, so I shouldn't take too much comfort in the fact that these numbers are low. There's nothing other than things that I am doing for personal protection that would contribute to that. And by that same token, when we look at the taller red bars, the off-campus students, it's easy to say, well, those darn off-campus students, they're the ones that are the problem. And that's not fair either, because the fact that you are in a dormitory doesn't offer any protection necessarily. And we have more people who are living right next to campus or near campus or so forth than are living on campus. And so we want to be careful about the way that we interpret these numbers, especially if we're going to say, oh, those people are the problem. And of course, the other thing that goes with this is if someone contracts COVID and they have to decide, where am I going to go? People who are on campus, who stay on campus and isolate, are going to be around fewer people than people who are off campus. And so if you know that you have to isolate for 2 weeks and you decide to go back home, let's say you're not from Springfield, you're from some outlying area, if you go back home, is the university kind of inadvertently helping to send that virus out into places that it wouldn't have been had you simply stayed on campus? So what we want to be sure of is that we're not making undue assumptions about the data. Another example that comes from this chart is we start on the left edge, we see the 42, 44, 35, we see that trend, which now looks like it's starting to decrease. However, if we model this using an exponential growth curve, in other words, what we would predict under exponential growth is the dotted line, what we see is that the reality is eclipsing the expectation. In other words, there are more cases than we would expect, and there's a natural inclination called regression toward the mean, that when you are above the mean, you tend to slide back toward the mean. And if you're below the mean, you tend to slide back toward the mean. A great example of this might be at Thanksgiving, when you are with friends and family. Hopefully we get to do that this year. And you gain a few pounds over the Thanksgiving break. So you go up 2 or 3 pounds, and then what happens within the week? You slide back to where you were previously. Regression toward the mean. The same thing is also true if you're trying to lose weight, so you lose 3 or 4 pounds, and then you're feeling pretty good about yourself, and then what happens? You tend to slide back toward the mean, back to where you were before. It's called regression toward the mean. It's a very natural occurrence, and that's what we're seeing here. And what this illustrates is that the bar chart might look like there is a decrease, but we want to have a reference point for comparison so that we know, are we truly decreasing the number of cases, or in this case, sliding back toward an expectation. So I want to show you this other example. It's called What We Know About the 20 Universities with the Most Coronavirus Cases. And I want to point out the author is Michael Netzel. Does that seem familiar to anyone? He says he is a former university president who writes about higher education. And if we scroll all the way to the bottom, we can see that he is a president emeritus of Missouri State University. So he's written this article for Forbes magazine. And it's well worth the read. It takes you through the top 20 universities and the number of cases. Now, Missouri State, we barely missed the 20 cutoff. There's the University of Missouri, Mizzou, up in Columbia. And this is just well worth the read. You can see what are the differences in schools where there are more or fewer cases. He's focusing specifically on the schools where there are more cases. So with that, I'm going to return to our lecture, and we're going to start with something that came up last week. There was a question about this level of significance or this critical value that we use in testing. So I told you about the null hypothesis. The null hypothesis, there is no difference between two means. We'll write that as mu1 equals mu2. No difference, they are the same. But then we said, we know that everything is going to differ if you go out enough decimal places. Everything is slightly different, even if it's just random. And so we want to have some kind of standard by which we say, if it is this different, then we're going to say it is truly different. So we used an example of two movies that had very similar ratings. One was 1 point higher than the other movie. And I asked, which one should we watch? Well, maybe we should watch the one with a higher rating. It's 1 point higher. It's got to be a better movie. And then we agreed that no, that 1 point difference isn't a real difference that matters. They are not significantly different. They're both the same level of bad. So how do we decide if a movie is truly better? Well, if it's 5 points higher, or 10 points higher, or 20 points higher, then we would say it was a better movie. There's enough of a difference that we would say it is truly different. So what I want to start with is, how do we decide what that cutoff should be, what that standard should be, that we say beyond this level, this critical value, these two means are truly and significantly different. So I want to start with our normal curve that I have divided, or let's say subdivided the two ends to an amount that we're going to become very familiar with. You probably have already heard about this, 0.05. So what I've done in this normal curve is I have taken 5% of the curve, and I've actually taken two sections of 2.5%, and I've put them on either end of the curve. That's the purple area. So what this is representing is we have 95% of our scores under that curve in the white area, the clear area, and 5% of our scores split into half, so 2.5 on either end. Those are the purple areas. The level of significance, or the critical value, is this fence that we use to determine if a test statistic is significant, or said more properly, there is a statistically significant difference. What the normal curve is representing here is all of the possible means that we could generate from a sample of a given size. So this is a distribution of sampling means. And there are some means that are so different from the population mean that we say they may occur by random chance, but more likely, those means are so different that they really, truly are significantly different. We start with our null hypothesis of no difference, and the fact is that most of the means that we might generate, just as a random sample, are going to be very similar to the population value. In other words, there is truly no difference between our sample mean and our population mean. And by definition, 95% of the time this will be the case, even with randomness. So in that white area in the middle of the curve, we have the area where we fail to reject the null. And that just means we stay with our original assumption of no difference. But it's not a real difference. It's not a difference that really matters. It's not statistically significant in its difference. But there are scores beyond the fence where we would reject the null hypothesis. The null hypothesis says there's no difference. If we reject the idea that there is no difference, we are saying that there is a difference. And that is our alternative hypothesis. So let me say that again. We start with the assumption of no difference between the means. And if we reject the hypothesis that there's no difference, we conclude that in fact there is a difference between those means. So how do we describe this critical value? We can describe it in terms of standard deviations, which is what the critical value truly is. We could describe it in terms of an alpha level or in terms of a cutoff score. And here's how we could do that. With a standard deviation, we might say that our critical value is 1.96 standard deviations. In the t-test example that we did, we found, we looked up a critical value, and it wasn't 1.96, it was actually a little bit larger than 1.96. That is still a critical value based upon a standard deviation. So the critical value that we look up in a table, or the critical value that we look up in that effect size calculator that I gave you, the Excel spreadsheet, which I really like because you just put in what's the degrees of freedom and it tells you the critical value. That is a critical value based on a standard deviation. The other way we can do this is with an alpha level, an alpha of 0.05. That is the alpha level that you should use unless you're told otherwise. So unless the problem says use a 0.01 or a 0.10 or a 0.076 critical alpha level, just stick with 0.05. So you're always safe. 0.05 alpha level, two-tailed test. That should be your go-to for all the tests that we do. But of course, because in this case, the normal curve is an actual set of numbers, those two fences would also articulate with an actual score on the x-axis, which in this case I've defined as 4.95 and 10.10. Those scores will differ for other distributions. So again, three ways that we can search for that cutoff score. Critical values, standard deviation, alpha levels, and the actual cutoff score on the x-axis. Now I know that that's a lot of numbers and math and so forth, so let me see if I can make it make a little more sense. I want to do that using an example of cow tipping. Now if you grew up in the Ozarks, you may have heard of cow tipping. And if you didn't grow up in the Ozarks, let me warn you, because let's say you're from, I don't know, St. Louis, and you come down to visit your friends here in the Missouri Ozarks, and they might say, let's go out cow tipping tonight. And what that means is we're going to drive out in the country, and we're going to hop over a fence and find some cows. You know, cows sleep standing up. And it would be really funny if we snuck up on the cows while they were sleeping and then pushed them over. Cow tipping. If you're familiar with the animated film Cars, I think it was Cars 2, tractor tipping, that's where that comes from. Okay, so you scare the tractors and they fall over backwards. Well, the same idea only with cows, except what happens is, especially if you're the person from St. Louis, all your friends from the Ozarks say, hey, let's go out to this field. And you think, okay, I'm kind of going along, and they're telling you what to do, and they say, jump over this fence and go run up to that cow and try to tip it over. Except what you don't know is it's not a cow, it's a bull. And bulls don't like to be disturbed when they're sleeping or otherwise. And this bull either wakes up or is already awake, noticed you sneaking in, and says, I don't want this person inside this fence with me, and that bull begins to chase you. And so you take off for the fence, where your friends are now laughing hysterically, and you've got to get over that fence in order to be safe. Does it matter to you if you are in the middle of the field versus right next to the fence in terms of being safe? You've got to be over the fence, outside the fence, in order to be safe from the bull. Now in this case, it's a cow. I couldn't find any pictures of bulls. This one I actually took out at my parents' farm, and there were some people who had cows that lived next door. So some great cow pictures here. I really enjoyed these. In these two examples, we see the cow is outside the fence. The fence is between you and the cow, or the bull, the very angry bull. If you're over the fence, you're safe. But if you are inside the fence in any place, not so safe. Here is the analogy with statistical significance. If a score is 0.051, if it's greater than 0.05, it's still inside the fence, not significant. Only if it is less than 0.05, so 0.049999 or less, is it outside the fence and is it statistically significant or different. Now you might quibble with that and say, well, wait a second, 0.051, 0.049, those really seem like they're the same, and you have a good point when you make that argument. And that's why we want to look at things like effect sizes, and we want to do power analyses, we want to understand the relationship between significance and sample size. But for the purposes of making a statistical decision, it's either less than 0.05 outside the fence, different, or it's greater than 0.05 inside the fence, not significant. That's how the decisions are made. Now, there will be more to that, as we will explore, but for this part of the statistical decision making, that's how we should interpret. Rejecting the null hypothesis if the sample mean is outside of the fence. The null says no difference. If you reject the claim of no difference, you're saying that there is a difference. So how do we select that level of significance? By default, we will use that 0.05 as our level of significance. Now we could set the level of significance to really any value that we desired. But for our purposes, we're just going to stick with 0.05. If we were doing medical research, we're going to see a lot of 0.01 levels of significance, because of medical research, the costs are higher in terms of the cost of making a mistake, of saying this drug works when in fact it doesn't work. This vaccine is effective when in fact it is not. So we're going to use a tighter restrictive level of significance, maybe a 0.01. And in political polling, where the cost of an error isn't that high, we might use a 0.1 level. And to illustrate this, I've used some coins. The 0.05 I've illustrated with a nickel, the 0.01 with a penny, and the 0.10 with a dime. And you can interpret your statistical tests using this allegory. Just think of a dollar, and a nickel is a 0.05 or 5 cents. So as you're doing your interpretation, as you're looking at your p-values, just convert them to cents. If it's a 0.032, well, what is that? 3.2 cents. That's less than a nickel. So that's statistically significant. If it's a 0.078, that's 7.8 cents. That's more than a nickel, not significant. So it might just be simpler to convert that to coins and think of it in those terminologies as you're trying to make those decisions. As you get used to using that 0.05, you're going to become more comfortable with that. But for now, feel free to think of it in terms of dollars and cents as you're making that decision. So now we're going to talk about the paired samples t-test, and more importantly, the interpretation of the paired samples t-test. So it's sometimes called a repeated measures t-test. See, repeated measures are when we have one group being measured 2 times. The best example of this would be a pre and post research design. So here you are, you're part of this experiment. We do a pre-test, which is like a baseline, and then we do the experiment, and then we measure you again post-test to see if there was a change. Did something improve? Did something decrease? Was there some change in that thing that we were measuring? So repeated measures, each individual is measured twice. We use the same subjects across the research, and an example might be we have a group of men who are weighed before and after an exercise program. These are called dependent measures as opposed to independent. Remember, we did independent samples t-test. These are dependent measures because the second measure depends on the first. So in this sense, each person becomes their own control group. Your after score, or maybe your after weight, depends upon your beginning weight. So we want to start with where you began and see how you changed over time. Repeated measures, we're measuring the same people more than once. Dependent measures, and all of these repeated measures are dependent. Your second score depends upon your first. Matched pairs. So this is the same kind of test, but we might design our research using matched pairs. That is, we have our experimental group, and we don't have someone, we're not going to measure them twice, but we are going to get someone else, a group of control subjects, who are very similar, and we're going to match them with each other to see what happens. This perfect example is the twin study. What we know about the twins is they are genetically identical. So what we would want to do is put them into two groups. We have one twin who is in the control group, and the other twin is in the experimental group. And we do some kind of experiment, and we see does the person in the experimental group improve or change, or are they different as the result of the experiment? And we're able to control for genetic differences. So that'd be one way to do that. Another way you might see matched pairs is we're doing some kind of study. It has to do with heart patients, but we need a control group, a comparison group. But we're going to match our people in the heart group, the heart patient study, with people in a hip replacement group. So what we're doing is we're finding people who are also in the hospital who've had a hip replacement, and we're matching them for, we need a male who is 60 years old, who's a non-smoker. We find all these characteristics, and that is, we start with the characteristic of the cardiac patient, and we find someone who's very similar from the hip replacement group, and we match them up. And we're going to follow both of them over time and see if there's a difference in an outcome, which should be occurring with the cardiac patients, but not occurring with the hip replacement patients. So we've matched those groups together. In all repeated measures testing, we are computing a difference score. That's just the difference between pre and post. So we start with your pre-weight, subtract your post-weight, there's the difference score. Therefore, with our null hypothesis, we could use the same old mu1 equals mu2, mu before equals mu after. But another way you will see this written is mu sub d equals 0, the mean of the difference. Sometimes you will see examples where the researcher will create that difference score and then test that difference score, as opposed to the way that I'm showing you, which is we have the pre and post and we're dropping both of those into the same model. So just different ways of approaching this type of test. So here's what a paired samples t-test design might look like. We're testing whether the average difference, the m or mu sub d, between the two means is statistically significant from 0. It's often used in before and after design. So there was a show, used to be on TV, called Biggest Loser. There were some reasons why that went off TV, but it was a good example of a pre and post design. So we have a group of people who are selected because of their weight, and we run them through a series of exercises and diet and changing lifestyle, and then we measure their weight afterwards. So what we have is one sample, one group of people. So if you think of this reality television show, it's the same people on the show. we measure their weight before, or their baseline coming into the program, and then we measure their weight after. If we have multiple measures, so if we're measuring week by week, we could do an ANOVA with that. But for our purposes, because we're talking about t-test, and remember T for 2, t-test always has 2 groups, whether it's repeated or independent samples. We're going to just take beginning and ending score. Other names for this test, this same test, so you will hear it called a matched sample t-test, a related sample t-test, a repeated measures t-test, or of course the paired samples t-test. Why so many names? It's really because statistics was getting its start in lots of places. So in America, yes, but also in Britain, and also in Russia, and also in Germany. And as the ideas were being shared across languages, the terminologies that one group was using would differ from what other groups were using, obviously differ through translation. And so there was just all of these names that emerged. They're all describing the same thing, the same design for this t-test, but you will hear different names being used. So for this last section, I'm just going to go through an interpretation of a paired samples t-test and show you the things to look for in the output. On the videos that I've created for you, you can see all the steps for doing this test in JASP. But this time I want to focus on the research design and the interpretation and how we would look at these numbers and what we would look for in the numbers. So here's our setup. You'll notice it's very similar to the one that we did with the independent samples t-test. Mickey is a dog trainer studying reinforcement effectiveness. He gets 16 puppies from 8 litters with 2 puppies from each litter. So we have a total of 16 dogs, and they're twins. We put 1 twin in each group. He matches each puppy in clicker training with its litter mate in food reward training. So again, we have 2 dogs from a litter. We put 1 dog in the clicker training group, the other dog goes in the food reward training group, and we're going to match them. We're going to see whether there is a difference as a result of the type of training. After training the puppies, he measures the number of correct responses by each on 10 exercises, meaning each puppy can get a score from 0 to 10. Was there a difference between the 2 training techniques as measured by this score of 0 to 10? Here's what you would look for in the output. Now this output comes from SPSS, but you will see the same layout in JASP. The biggest difference would be that the table that I have at the bottom of this slide for the paired sample t-test is going to be at the top of the JASP output. But the other parts you will see except for paired samples correlations, which do not appear in the paired sample t-test output in JASP, but you can actually run the correlation, and you might want to do that if you were using a correction on the effect size. We want to know, are these results telling us that the test is significant or not? 3 things that we can look for. Number 1, look at that confidence interval. It does not cross 0. So what do I mean by that? Well, the lower boundary is a 0.17 and the upper boundary is a 2.3. Both of those are positive, which means there's not a 0 in between them. Same thing would be true if they were both negative. If they were both negative, there's not a 0 in between them. It's only when one is negative and one is positive that it crosses 0. So in this example, the confidence interval does not cross 0, does not include that hypothesized difference of 0. Therefore, this test is statistically significant. The second thing I could look for is the t-value. In this case, the t-value is a 2.758. And if I used either my t-table or that effect size calculator, and I entered 7 degrees of freedom, I would get a critical value of 2.365. So roughly 2.3 is my cutoff. My t-value is 2.7. So my t-value is over the fence. It's outside the fence. It is greater than that cutoff, making this test statistically significant. The third thing I could look for is my p-value, which in this case is going to be labeled as an SIG, stands for significance. It is a 0.028. Well, 0.02, that would be what? 2.8 cents. Is that less than a nickel? Yes, it is. So it is less than 0.05, telling us that this test is statistically significant. All three of these tell us the same thing. They will never diverge. There will never be a time when one or two are telling you the same thing and one is telling you something different. All of these converge on the same idea that these results are statistically significant. So there is a difference between these groups. We started with a null hypothesis that said no difference, but in fact, we have rejected that hypothesis. We have rejected the hypothesis of no difference, concluding in fact that there is a difference. Statistically significant means that there is a difference in the means. Sir?
How do you get the CV here? Because I don't.
Right. So the question is, how did I get the critical value? And that I would look up in a table. There is a t-table at the end of your notes. Or I could look it up I've included a table in that effect size calculator. Or the best way, I think, is use the effect size calculator. There's a second tab that says critical value, and there's a box. And you enter the degrees of freedom, and it tells you the critical value. There's one more thing that I need to tell you about. This is going to be important for the unit test. So upcoming, we're going to have a test that covers the first 4 weeks, which will include the independent samples t-test and the paired samples t-test. Everything on that test is going to be exactly what you've done already. So if you can do an independent samples t-test in JASP following the examples from the video, if you can do the same thing with a repeated measures t-test following the examples from the video, that is exactly what you will do for the unit test. There'll be no difference. It's designed to be the same. But you want to be sure that you know what to do with these data, because there's something you have to do with the independent samples t-test that you don't with the repeated measures t-test. It has to do with how we set up the data. So the data for the two tests, for independent versus paired, are set up or structured differently. And you may have encountered this. If the structure of the data is wrong, you can't run the test that you want to run. So if you try to simply import the Excel spreadsheet into JASP and it was structured weird, it's not going to run the independent samples t-test. You have to restructure the data. Why did I do that? Because that's how a lot of the data will arrive to you. You need to be able to restructure those. So you need to think about what kind of test you're going to run before you enter the data, and then enter them in the way that you're actually going to use them. For the independent samples t-test, you're going to have one continuous variable or scale variable. In this example, it's score. And then you have one categorical variable. In this case, it's group, 1 and 2. So we have two groups measured one time. For the repeated measures, or paired samples t-test, you will have two columns, each with scale level data. In this case, the scores. So we have the before and after scores, or with the puppy example, we have the clicker versus food reward, or with the example that we'll be doing this week, is math scores being compared to writing scores for the same person. And this is true for any independent or repeated measures design, whether we're doing a one-way ANOVA, in which case we would have a set of scores and we would have 3 groups, 1, 2, and 3. Or if we were doing a repeated measures ANOVA, which is the extension of the paired samples t-test, we would have before and after and then maybe 3-month follow-up. We would have 3 columns of scale data. So we will always set up repeated versus independent samples in exactly the same way. It's just the complexity of the test. In this example, this being the puppy training example, I used the same data from last week as I did for this week. So the numbers, the means and standard deviations, are going to be exactly the same, but we got 2 different outcomes. What I mean by that is the independent samples t-test was not significant, but the same scores in a repeated measures t-test were significant. Why does that happen? Because the repeated measures t-test is more powerful. What that means is it's easier to find a difference if it exists using repeated measures than it is independent measures. Now this will become important toward the end of the course when I talk about power analysis. What does that mean? It's simply how many people do I need to have per group in order to increase the likelihood of finding a statistically significant difference. So how many people do I need to have per group? It's a power analysis. And we'll go into much more detail when we get to that part of the class. So do you have any questions about the paired samples t-test?
I just have a question about the test.
About the test, that's good too.
When's that due?
When is it due?
Yeah.
Okay, so here's how the test thing will work. What I'm doing is going by units. So the first 4 weeks and then the test. And for this first unit, because we're all still trying to get everything figured out, what I'm going to do is leave that open for 5 weeks. So get the first 4 weeks assignments done, and then you will have next week, week 5, we're going to have a shorter, a less intensive set of material from the textbook, maybe half as much as we might from these previous weeks. And you have all week to study for and prepare for the test itself. So there will be a study guide that will tell you what's on the test. I will have the data sets. So you'll have 2 data sets. You'll have to decide which one is paired, which one is independent. You have to run the test just like we did in JASP. You'll have the answer sheet where you can write down your findings. And then there will be a set of, know this topic. What does this mean? How many groups do we use? That kind of study guide. So you could study up on everything that we've covered. Once you have those ideas in your mind of here's the answers, and then you have your findings from the t-test, you'll click on the button, open up the test, enter your findings, answer the true, false, multiple choice questions, and that's it. And that will be due at the end of week 5. So Sunday night, midnight, into week 5. So that gives you a maximum amount of time. Again, I really want you to learn. It's easier for me if you know this. If I have to kind of drag you along, right? It's a lot more work for me. So if you actually get this information, it's going to be a lot easier for you, a lot simpler, more fun to get through this class. And I'm really interested in your learning this. I would love for you to go on to other classes, and when the topic of statistics comes up, you know this stuff. You got this down because you took the time to really learn it. And so you'll be the person in that class that everybody looks to for the statistical guidance because you really know this stuff. That's what I want for you as a result of taking a class like this. All right. Well, thank you so much for being here. Be safe, and I'll see you guys next week.